Thank you, Fangping. Hello, everyone. So now that we have shown the possibility of coordinating knowledge-driven policies from a single central point, we now delve more into realistic network scenarios. So the one I want to discuss is like in interdomain routing. So we show an application which we like to call policy exchange. So before we dive more into policy exchange, we want to show a small overview of Border Gateway Protocol or BGP. So autonomous systems are networks that exist that are managed by single enterprise or service providers. And Border Gateway Protocol communicates between these autonomous systems. It routes packets it takes routing decisions for packets, and it is a shortest path routing protocol. And it also makes routing decisions favoring autonomy. So why policy exchange? So as I discussed previously, BGP favors autonomy. Policies are made based on local preferences, and it may cause unwanted interaction between policies. I'll give you an example of what I mean. So we have this diagram where there are 6 nodes, and we have node X, which has a policy that says it requires only routes with no more than 3 hops to the destination 1.2.3.4, which we can see connects to node E. And there is also another policy at node A which balances traffic for its neighbors C and D. So now we see that if X wants to reach 1.2.3.4, it has 2 paths. So the first is the valid path, which is X via A, via C, via E. And this satisfies both the policies at X and A, because it takes less than 3 hops to reach from X to E, X to 1.2.3.4, and it also balances traffic at node A between C and D. Now if the other path is taken, which is X, A, D, B, E, even though it balances our even though it satisfies our traffic balance policy at node A, it does not satisfy our requires no more than 3 hops policy at node X. So this is not wanted by us. This is an unwanted. So we require to make a proper decision. So we approach policy exchange. So how do we do this policy exchange? So we take the same diagram from our previous example, and we show these 2 policies in terms of our policy tables using conditional tables. So we have our first policy at node X, and we see that we have a condition here that Lx should be less than equal to 3, which denotes the hop count. And we also have our conditional table. We also have our policy table at node A, which has the conditions based on the flags U and V, such that both of nodes C and D should not be carrying traffic for the same node at any point of time. So now the policy at X is propagated to the node A, and we can see that it changes to Lx is now less than equal to 2, because we already have 1 hop count towards reaching from node X to node A. After that, we do the merging, where we merge the 2 policies, the one that came in from node X and the other one that is already the policy of node A. And we can see we now get the policy something like this, and we see that we have now 4 tuples, and the first tuple is the connection between the 2 policies, and U is now equal to 1, but we also have the additional condition of Lx being less than equal to 2, and same for the next line. But among these 4 tuples, we see that our second line is not satisfied, because if our next hop is D, then our Lx will not be less than equal to 2. So we remove that line, and now we have 3 satisfactory tuples. We have the first one where traffic to 1, 2, 3, 4 will go via C, and traffic through 5, 6, 7, 8 will go via D. And we also have traffic to 5, 6, 7, 8 going through C when U is not equal to 1. That is when there is no traffic to 1.2.3.4. So we currently have our preliminary prototype, which uses in-memory implementation in terms of Python lists. So we have real-life applications such as policy exchange, which I explained just now, and we also have BGP simulation, which mimics the behavior of a BGP speaker as it receives announcement from its neighbors. So we have used the benchmark, which is the MRT format, RouteView BGP data. We have used the ribs and updates from RouteView to Oregon, and we have generated synthetic policies and realistic topologies to test upon. And we have now showed the performance of our relational operators. We have chosen 3 for this demonstration. We have shown the comparison between projection operator, selection operator, and one join operator. So we can see the projection operator performs the fastest, followed by a selection operator, and then we have the join, which is a join between 2 policies, P1 being static route and filter policy, and P3 being traffic balance policy, and we do a join between those 2, and we can say that our projection is the fastest, followed by selection, followed by our join performance. And now we pick the scalability for our join function, the one we discussed in the previous slide, and we see that when we increase the size of the policy table, our time required also increases. I mean, our overall time required, but this overall time is dominated by our SMT solver, that is our Z3 solver. So SMT solver takes 96% of the running time. We can also see that our implementation can handle 10,000 policies in a little over 70 minutes. So we have more policy examples. For example, that we show, that is P1, we can see in the diagram, is the static route policy, P3 is the traffic balance policy, P4 is the filter policy. We also show the total time, and we can see that it being again dominated by our SMT solver. So we have the primitive that validates a relational policy. We call it POS SP, which is a relational policy P on a given network state S. And we have the running time, which is, and we can see there that P3 is faster than P1, which is again faster than P4. And we also see that SMT, like I said, dominates the source of our delay. So we have related works, which is like interdomain routing protocols and architectures. We have DBGP and Trotsky, which they work by partial deployments of the protocols, and they require their coexistence on the global internet in order to function. We also have related works in declarative networking. For example, like we share database usage in networking, but we have introduced and implemented a novel use of conditional tables. Thank you so much for your time. For more information, you can either visit the website ravelnet.org, or you can check out our paper. Thank you so much.